Have you ever found yourself lost in deep questions, trying to solve the puzzle of reality? Today, we'll explore the depths of the mysteries that appear when we try to piece together this enigmatic puzzle. If Boltzmann brains are theoretically possible, why do we experience a consistent and continuous reality? If a particle in superposition can exist in all possibilities, how valid is the single reality we experience? How is quantum entanglement related to the structure of space-time? Does synchronicity imply a connection between consciousness and the universe beyond scientific explanations? Does the butterfly effect make it impossible to fully know reality? Can a two-dimensional surface truly store all the information about a three-dimensional universe? Is our perception of space and time simply a product of how our brain interprets the universe? If time is an illusion, what is death? Let's delve into the answers to these questions with a comprehensive scientific perspective. The Boltzmann brain paradox questions whether the likelihood of a brain spontaneously appearing with false memories due to random quantum fluctuations in an infinite universe is greater than the probability of a real, continuously functioning human brain evolving naturally. According to this idea, if the universe is infinite, over time, random and rare events could occur anywhere in the universe as a result of thermal and quantum fluctuations. One of these events could be the sudden appearance of a brain with false memories and brief consciousness. Boltzmann brains are envisioned as structures that only exist for a short time and are filled with illusions of living a human life. However, these brief consciousnesses would not be the result of a regular life process, but entirely random. The main question of the paradox is whether the probability of the formation of these brains is higher than that of real human brains, which have evolved through long-term processes. The probability of a Boltzmann brain forming is considered much lower than that of a real human brain for several reasons. First, Boltzmann brains are momentary structures formed randomly due to quantum fluctuations or thermal perturbations. However, a brain is an extremely complex structure and requires highly precise neural connections to function properly. A real human brain, on the other hand, has developed step by step through evolutionary processes over billions of years, influenced by biological mechanisms and environmental factors. Additionally, according to the second law of thermodynamics, the entropy or disorder of the universe always increases. Therefore, the spontaneous formation of a highly organized and complex structure like a Boltzmann brain through random processes is extremely improbable. A real human brain has attained its complex structure through long-term, natural processes, making it much more likely than a chance occurrence. If you were a Boltzmann brain, it would be extremely difficult, if not impossible, to distinguish between a real existence and a fleeting illusion. The key feature of Boltzmann brains is that they are filled with false memories and exist for a brief period. In this case, all the memories you have, your childhood, your loved ones, the events in your life, would not have actually occurred, but they would seem entirely real to you. These false memories and momentary consciousness would mimic the experience of real life so well that it would be impossible to tell the difference. The difficulty in distinguishing between them lies in the fact that our conscious experiences are based on verifiable external references. If you were a Boltzmann brain, everything you knew about your surroundings and past would already be constructed in your mind, and there would be no external reference point to validate these memories. Unlike real existence, this experience would be so brief that any search for consistency or continuity would be futile. The real challenge is that even the act of questioning yourself could be part of this fleeting illusion. Therefore, your ability to differentiate between reality and illusion would be limited by the brief existence of the brain. This deepens the paradox. Even if you were aware of the illusion, you might not have a reliable tool to test the reality you are experiencing. So, if we were Boltzmann brains, how do we experience a consistent and continuous reality? There are several hypothetical explanations for this. One possibility is that reality itself is an illusion. In other words, if we were Boltzmann brains, since all our memories and experiences would already be false, the perception of a consistent and continuous reality could also be an illusion. Since the Boltzmann brain only exists for a short time, past and future experiences would be created in the mind. This would mean that the continuity of life you believe you are experiencing might actually be taking place in just a few seconds of consciousness. Another possibility is that the emergence of Boltzmann brains is extremely rare. In most parts of the universe, entities that experience consistent and continuous reality might be predominant. In other words, if Boltzmann brains form rarely in the universe, we could be entities that were formed through natural processes and are not affected by these random fluctuations. While Boltzmann brains may remain rare and temporary anomalies in the ocean of probabilities in the universe, regular beings continue to exist through evolution and physical laws. A more speculative explanation could relate to the multiverse theory. If there are an infinite number of universes, there could be universes where Boltzmann brains emerge. However, we might not be in one of these universes, but rather in one where brains formed naturally through biological evolution. Our experience of a consistent reality could indicate that we are in a universe where order, not random fluctuations, governs the formation of conscious beings. Finally, we may have incomplete knowledge about the nature of consciousness and reality. Even if we accept that Boltzmann brains are mathematically possible, our continuous experience of a consistent reality might be explained by a mechanism beyond our current understanding of consciousness and existence. Perhaps consciousness operates according to regulatory principles, rather than random fluctuations, allowing us to exist as beings with continuous consciousness. In conclusion, one or more of these reasons could explain why we experience a consistent and continuous reality in a universe where Boltzmann brains are theoretically possible. Superposition in quantum mechanics refers to the ability of a particle to exist in multiple states or positions simultaneously. This is quite different from classical physics, where an object is either in one place or another. It cannot be in two places at once. In the quantum world, however, for example, an electron can be in both the spin-up and spin-down states at the same time, or a photon can take different paths simultaneously. This phenomenon is explained by the overlap of probabilities described by the particle's wave function. In other words, before the particle is observed at a specific point, it behaves as if it exists in all possible locations and states. This continues until the particle is observed, at which point its wave function collapses and only one state emerges. Therefore, superposition represents the broad spectrum of quantum possibilities a particle can have. A particle in superposition can experience all possibilities at once. That is, the particle does not have a definite state. In other words, the particle exists as a mixture of all possible states. For example, an electron can be in two different energy levels around an atom at the same time, or a photon can travel along two different paths simultaneously. This means the particle experiences not a single reality, but all possible realities at once. However, when this situation is observed or measured, the superposition ends, and the particle collapses into a single state. This essentially means that the process of experiencing all possibilities ends with observation, reducing it to a single reality. Before observation, an objective reality does not exist. Instead, there is a collection of possibilities. Only when the observer comes into play does a single result emerge at the quantum scale. The role of the observer in superposition is one of the most important discussions in quantum mechanics. The effect of observation on quantum systems is known as the measurement problem. While a particle is in a superposition state, it contains all possibilities at once, but the moment it is observed, only one of those possibilities occurs. This process is called the collapse of the wave function. In other words, the observer influences the quantum system, causing the system to produce a single, definite outcome. The classical Copenhagen interpretation suggests that the observer or measuring device causes the superposition to end, and the system collapses into a single state. According to this, quantum systems remain in states of uncertainty and superposition until they are observed. But during the moment of observation, one state becomes definite. The single reality we experience is not an average of all the possibilities in superposition, but rather the result of this wave function collapse. Before observation, the particle is mathematically represented by probability distributions, but after observation or measurement, this distribution collapses and a single definite result appears. Therefore, we do not experience a combination of the possibilities in superposition. Rather, we experience only one of them, which results from the collapse. The reality we experience represents the resolved form of these quantum uncertainties. In other words, in our macroscopic world, we do not observe the different possibilities of a particle in superposition. We only experience the single outcome resulting from this collapse. That is, while superposition exists at the quantum level, in the classical world, our observations are always reduced to a single result. Ultimately, quantum collapse is the process by which an uncertain and multi-possibility state in the quantum world ends with observation or environmental interactions, leading to a single experienceable reality. This helps us understand the mechanism behind the certain and definite realities we observe in daily life. How does the single reality we experience get affected by quantum uncertainties? The influence of quantum uncertainties on the single reality we experience relates to how quantum uncertainties and probabilities manifest in our macroscopic world. At the quantum level, particles are described by probability distributions rather than precise positions and velocities, implying an inherent uncertainty in the nature of reality. However, we do not directly experience these uncertainties in the macroscopic world. This is because quantum effects generally remain confined to very small scales, and classical physical laws dominate on larger scales. In certain cases, though, quantum uncertainties can affect the macroscopic world, as in thought experiments like Schrödinger's cat, where the state of macro objects can be determined by quantum superposition. Nevertheless, in everyday experience, reality mostly seems like a single path, because quantum probabilities collapse upon observation, forming a definite outcome. Thus, while quantum uncertainties have an indirect impact on the reality we experience, these effects are generally confined to observation. The multiverse theory offers a radical explanation for quantum superposition. According to this theory, all the possibilities that exist when a particle is in a superposition state actually occur, but each possibility happens in a different universe. In other words, while we experience one possibility, other possibilities are realized in parallel universes. This approach is known as the many worlds interpretation, which argues that the wave function does not collapse, but instead, every possibility is realized in separate universes. According to this theory, the reason we experience only one reality is that we are part of that particular universe. The other possibilities continue independently in other universes. The fact that superposition encompasses many possibilities that we do not directly experience could greatly expand our understanding of reality. Traditionally, what we call reality is considered to be the sum of definite and specific events. However, quantum superposition shows that many possibilities can exist at the same time and that we only encounter a single outcome during observation. This suggests that the universe is not limited to a single, definitive reality based on our observations, but that a broader field of possibilities exists beyond observation. Possibilities that we do not experience might still exist in the quantum world, and reality could have a far more complex and flexible structure than we currently perceive. This understanding pushes the boundaries of objective reality and might require us to be more open-minded about the true nature of the universe. Classical physics and Einstein's theory of relativity propose that interactions between 2 points in spacetime are limited by the speed of light. This principle asserts that no information can travel faster than light, and all interactions occur within this speed limit. However, quantum entanglement challenges this limit and raises important questions about the nature of the physical world. In quantum entanglement, once two particles become entangled, any change in the state of one particle instantaneously affects the state of the other, even if they are separated by vast distances. This instantaneous interaction is non-local, meaning that the expected spacetime distances in classical relativity are disregarded. While this is not considered a transfer of information faster than light, it is a phenomenon that cannot be explained by the rules of classical physics. This suggests that the structure of spacetime is not as fixed and constrained as we might think in classical physics. Non-local interactions indicate that the geometry of spacetime could be far more flexible than previously believed. For instance, classical physics' principle of causality assumes that any interaction between two objects depends on their distance and time delay. However, in quantum entanglement, such distances and time delays lose their meaning. This points to the possibility that space and time are not absolute concepts. Rather, they could be dynamic constructs shaped by deeper, possibly more fundamental processes at the quantum level. The fact that non-local effects occur so rapidly suggests that there could be an underlying connection structure beneath spacetime. In this context, some theories propose that quantum entanglement could play a fundamental role in the formation of the fabric of spacetime. Approaches such as the holographic principle suggest that spacetime could be constructed through quantum entanglement relations. and that such entangled processes are part of the fundamental structure of spacetime. According to this principle, the three-dimensional structure of the universe is actually composed of information encoded on a two-dimensional surface. In other words, all physical processes in the universe could be described not within a three-dimensional volume, but on a two-dimensional surface that surrounds it. When combined with quantum entanglement, the holographic principle suggests that the structure of spacetime could be shaped by entanglement relations on this two-dimensional surface. In this sense, quantum entanglement is viewed as a tool for probing the foundations of spacetime. The holographic principle proposes that everything in the universe is a projection of information encoded on a two-dimensional surface, and quantum entanglement relations on this surface help shape the fabric of spacetime. Specifically, theories such as the correspondence between anti-de Sitter space and conformal field theory exemplify the holographic principle. This correspondence suggests that a quantum field theory defined on a boundary is equivalent to a gravitational theory involving spacetime. The relationship between anti-de Sitter space and conformal field theory represents an important step in explaining the connection between gravity and quantum mechanics in the universe. The relationship between quantum entanglement and the holographic principle implies that spacetime itself could be constructed from degrees of entanglement. Some theoretical physicists even argue that the structure of spacetime and the dynamics of gravity emerge from quantum entanglement. According to this view, if the degrees of entanglement in certain regions of spacetime are disrupted, this disruption could lead to changes in the structure of spacetime itself. Entanglement plays a critical role in organizing spacetime structures and determining the dynamics of gravity. The holographic principle is also directly related to quantum information theory. Quantum entanglement is linked to physical phenomena such as black hole entropy, where the holographic principle can be applied. The work of Stephen Hawking and Jacob Bekenstein showed that the entropy of a black hole is proportional to the surface area of its event horizon. The holographic principle suggests that the information on this surface, via quantum entanglement, could contain all the physical properties of the black hole. This demonstrates that physical information in any region of the universe could be encoded through entanglement relations, showing the deep connection between spacetime and quantum information. Quantum entanglement also plays a crucial role in theories of quantum gravity and the quantum structure of spacetime. Classical general relativity assumes that spacetime is a continuous, smooth structure with well-defined properties at every point. However, quantum mechanics reveals that matter and energy at the quantum level are granular, meaning they are discrete and filled with uncertainties. In this framework, spacetime is thought to be discontinuous, dynamic, and intertwined with quantum entanglement at the smallest scales. The goal of quantum gravity theories is to explain the force of gravity at the quantum level. Classical general relativity explains the structure of spacetime at large scales and describes gravity as the geometric curvature of spacetime. But quantum mechanics suggests that this continuous structure breaks down at very small scales, such as the Planck scale, and becomes more granular. At this level, the structure of spacetime may no longer be smooth, but can instead be described as a kind of quantum foam shaped by quantum entanglement. This concept of quantum foam indicates that at very small distances, such as the Planck length, spacetime is not continuous but discrete and dynamic. Quantum entanglement could be a key factor in constructing this discrete structure. In some theories, the structure of spacetime is thought to emerge from the interactions of entangled particles. That is, the fabric of spacetime may be constructed through the dynamics of entangled quantum particles and quantum processes. According to this view, spacetime itself could be thought of as a network formed by quantum entanglement. Entanglement offers a window into understanding how spacetime is fundamentally formed and structured. Quantum entanglement plays a crucial role in understanding the quantum structure of spacetime in two main ways. First, the relationship between entangled particles may form the binding fabric of spacetime. This idea is emphasized particularly in theories like the holographic principle and the correspondence between anti-de Sitter space and conformal field theory. The holographic principle suggests that everything in the universe originates from information on a two-dimensional surface, and the entanglement relations on this surface shape the three-dimensional structure of spacetime. Second, quantum entanglement provides insight into how spacetime operates at the quantum level. These relationships between entangled particles offer significant clues about the behavior of spacetime on small scales. In particular, these entanglements that arise in the structure of spacetime at the quantum level could be critical in understanding the relationship between gravity and quantum processes. These two mechanisms enable us to explore how spacetime operates at the most fundamental level and uncover the connection between quantum mechanics and general relativity. One of the quantum gravity theories, loop quantum gravity, argues that spacetime has a discrete and granular structure. According to this theory, spacetime consists of small, discrete particles, loops, and the connections between these loops are related to quantum entanglement. In this context, the structure of spacetime is shaped by a network of quantum entanglement, and at the quantum level, these entanglements determine the dynamics of spacetime. The relationship between quantum entanglement and Einstein-Rosen bridges, or wormholes, is a significant theoretical area exploring the connection between quantum mechanics and general relativity. This relationship is explored through a hypothesis linking Einstein-Rosen bridges and the Einstein-Podolsky-Rosen paradox of quantum entanglement. The hypothesis suggests that there is a fundamental relationship between entangled particle pairs and wormholes in spacetime. Simply put, an entangled particle pair could behave like a wormhole in the structure of spacetime. Einstein-Rosen bridges are theoretical structures in general relativity that connect two different regions of spacetime via a tunnel-like path. These bridges theoretically offer a shortcut between distant points in space. However, in classical relativity, it remains uncertain whether any matter or information could pass through these wormholes intact. The Einstein-Podolsky-Rosen paradox, on the other hand, is a thought experiment that discusses quantum entanglement. No matter how far apart two particles are, measuring the state of one particle instantly affects the state of the other. This is explained by the non-local interactions of quantum entanglement. In this context, quantum entanglement and wormholes could be fundamentally connected to understanding the structure of the universe. The relationship between two entangled particles could be thought of as behaving like a wormhole in spacetime. This hidden wormhole between two entangled particles may act as a bridge carrying quantum information instead of physical matter. This hypothesis reinterprets the topology of spacetime through quantum entanglement. The bridges formed between pairs of entangled particles could be fundamental components of the structure of spacetime. Thus, spacetime could be seen not as a smooth and continuous structure, but as one shaped dynamically by entanglement relations. This theory goes beyond speculation about wormholes and entanglement, offering a potential way to understand the connections between quantum information, gravity, and spacetime. If this hypothesis is correct, quantum entanglement could form physical bridges in the smallest scales of spacetime, providing a fundamental method for bridging quantum mechanics and general relativity. In classical science, local realism is based on the assumption that physical systems can only be described by properties measurable in their immediate vicinity. Distant objects cannot contribute to the reality of the local system, and interactions are measurable only within this local environment. This understanding forms the basis of classical scientific reductionism. In contrast, in quantum physics, non-locality shows that distant physical systems can be inseparably connected and form a single quantum system. This connection, while not measurable at the local level, means that the whole system cannot be regarded as separate and independent parts. Such connections are explained by phenomena like quantum entanglement and synchronicity. The principle of synchronicity emerges as a new method of inquiry, challenging the limits of science by relying on the concept of non-locality. This approach, developed to understand mysterious phenomena like quantum entanglement that cannot be explained by classical reductionist experiments, fundamentally shakes our view of the universe. It proposes that events in the universe can be explained not only by local effects, but also by broad interactions and interconnections. Thus, the deep connections between events open new horizons beyond the current methods of science. This expanded scientific perspective leads us to rethink the connection between consciousness and quantum information. The idea that our consciousness may be based on quantum information processing transforms consciousness from being merely a passive observer into an active processor at the quantum level. According to this model, consciousness could be an element shaping reality by processing quantum information. Just as quantum computers collapse upon observation, consciousness could affect the dynamics of reality through conscious choices. This thought prompts us to reevaluate the role of consciousness, suggesting that events in the universe are not random, and that there may be a deep connection between consciousness and reality. At this point, the weak and strong versions of the anthropic principle add a new dimension to this idea. The weak anthropic principle argues that our place in the universe must be compatible with our existence as conscious observers, while the strong anthropic principle posits that the universe must have properties that allow for the existence of conscious observers. When combined with the idea that quantum consciousness shapes reality, these principles imply that the universe may not be randomly arranged, but intentionally structured for conscious life. This order in the universe can be likened to solving a Rubik's Cube. Finding the correct solution with random moves has a very low probability, but with an intelligent guide, the cube can be solved much faster. Similarly, the perfect harmony in the universe, allowing life and consciousness to emerge, may point not just to randomness, but to an evolutionary process guided by conscious choices. This supports the idea that behind the process of evolution, there could be a kind of conscious guidance, much like quantum consciousness. Theories allow us to reconsider the nature and evolution of the universe. This expanded perspective on the relationship between consciousness and quantum information positions consciousness not just as a perceiving mechanism, but as a fundamental ontological element of the universe. In this model, consciousness is considered one of the most fundamental building blocks of the universe, closely linked to quantum information processing. The idea that consciousness actively shapes reality at the quantum level allows us to question the deep connections between consciousness and reality. In this context, it brings to the forefront the idea that events in the universe are not purely random and that conscious choices play a crucial role in the universe. In this framework, conscious agents are thought to self-organize from the quantum vacuum, starting from the simplest forms of consciousness to more complex systems with higher levels of awareness. Fundamental particles in this model are considered simple forms of consciousness, and over time, these particles form more complex structures, reaching higher levels of awareness. In this approach, conscious processes are thought to work similarly to quantum information processing, with qubits used to model states of consciousness. It is suggested that the universe, like a quantum computer, processes quantum information to guide states of consciousness. Anthropic principles are also consistent with this thought. The strong anthropic principle argues that the universe is structured in such a way that conscious observers can develop. This implies that conscious beings in the evolutionary process may have been guided not by randomness, but by conscious choices. Using the Rubik's Cube analogy, the idea that the perfect alignment of conditions in the universe could have been shaped by conscious guidance strengthens the understanding that consciousness is a fundamental element in the complex structures of the universe. In this context, the connection between some basic forms of consciousness and known particles, such as quarks, leptons, and bosons, offers an important clue for understanding how consciousness manifests in the material universe. However, more mysterious forms of consciousness, which could be defined as non-local elements of consciousness, are also present, and these could be associated with elements that cannot be directly observed, such as dark matter and dark energy. These non-local elements of consciousness offer a new perspective for understanding astrophysical phenomena that cannot be explained by classical scientific methods. This new viewpoint creates a thought framework that is consistent with the anthropic principle. While the strong anthropic principle suggests that the universe is designed to allow conscious observers to emerge, consciousness may not be limited to known material structures, but may also be associated with mysterious elements like dark matter and dark energy. These non-local consciousness elements, undetectable by local observations, might constitute the building blocks of dark matter and dark energy. Just as in the Rubik's Cube analogy, these hidden structures of the universe might also have been shaped by conscious guidance or choice, suggesting that consciousness could be the key element behind the complex order of the universe. Current quantum physics experiments, especially those with mesons, indirectly support the principle of synchronicity. For example, in experiments with entangled meson pairs, the decay of one meson instantly determines the state of the other. These types of experiments embody the fundamental characteristics of the synchronicity principle, as an action applied to one part of the system creates an instantaneous effect on the distant part. In the future, synchronicity-based experiments have been proposed to test non-local effects. In these experiments, local actions are applied to different parts of entangled systems, and changes occurring in the other parts are observed. These experiments could test whether, as predicted by the synchronicity theory, an action performed in one part of the system causes instantaneous changes in a distant part. Quantum computers play a significant role in processing synchronous information, as quantum computers manage quantum information processes and, unlike classical computers, can process probabilities in superposition. This feature could be used to understand and guide the evolution of consciousness. Quantum computers could be a tool to understand how conscious processes work and to conduct more complex synchronicity experiments. Challenging traditional scientific understanding begins by proposing that space-time and material reality are secondary structures created for human consciousness to perceive the universe sequentially. This approach questions the assumption that scientific laws are fixed and universal, because these laws are valid only within the framework created by human consciousness to understand the universe. The principle of synchronicity posits that consciousness is a primary and fundamental element of the universe. Each level of consciousness is characterized by its own reality and laws, suggesting that every level in the universe has its own rules. This principle argues that consciousness precedes material reality and that all events in the universe are interconnected. Quantum physics and synchronous science help us understand the evolution of the universe and consciousness in a more holistic way. These approaches show that everything in the universe is interconnected and that non-local effects play a significant role. The principle of synchronicity offers a new approach to scientific inquiry, suggesting that events can be understood not only through local, but also through universal connections. Thus, it introduces a transformative understanding of scientific research, providing a broader perspective on scientific methods. In the late 18th century, French mathematician and physicist Pierre-Simon Laplace proposed a groundbreaking thought experiment about the nature of the universe. Known as Laplace's deterministic universe, this idea argued that the universe is entirely predictable. Laplace imagined a superintelligent being that could know the position and momentum of every particle in the universe. This hypothetical being is also known as Laplace's demon. According to Laplace's view, if this superintelligent being knew the precise state of every particle in the universe, it could use Newton's laws of motion to predict both the past and future with absolute certainty. This is a philosophical view known as strict determinism, reflecting the idea that every event in the universe is entirely governed and predictable by physical laws. This view was inspired by the successes of Newtonian physics. Newton's laws of gravity and motion allowed the prediction of planetary movements with great accuracy. Laplace believed that this success could be extended to all aspects of the universe. In his view, nothing in the universe was random. Everything was the inevitable result of preceding events. Laplace's idea formed the foundation of scientific determinism and remained the dominant view in the scientific world for many years. It supported the notion that science's ultimate goal was to solve all the mysteries of the universe and make everything predictable. By the mid-20th century, scientists began to realize that Laplace's deterministic view of the universe had some serious limitations. This realization led to the birth of chaos theory. Chaos theory is a field of study that examines the behavior of dynamic systems and shows that small differences in initial conditions can lead to large and unpredictable outcomes over time. The core principle of chaos theory is that even though a system may be deterministic, its long-term behavior can be unpredictable. This might seem paradoxical at first. How can a system governed by exact rules produce unpredictable results? The beauty and complexity of chaos theory lie in this very question. Chaos theory manifests particularly in complex, interconnected systems. For example, weather, ecosystems, financial markets, and even the human brain can exhibit chaotic behavior. In such systems, small differences in the initial conditions can magnify over time, eventually leading to vastly different outcomes. Chaos theory operates through non-linear equations. These equations show that the relationship between inputs and outputs is neither simple nor direct. Instead, the variables within a system are intricately interconnected, constantly influencing each other. These complex interactions make it difficult to predict the system's behavior over time. Perhaps the most striking and popular concept in chaos theory is the principle of sensitive dependence on initial conditions, also known as the butterfly effect. This term, coined by American meteorologist Edward Lorenz, refers to the idea that a butterfly flapping its wings could theoretically cause a hurricane on the other side of the world. Sensitive dependence on initial conditions means that in a system, very small differences at the start can lead to vastly different outcomes over time. This principle is a key feature of chaotic systems and explains why long-term predictions in such systems are incredibly difficult. The butterfly effect can be an intuitively challenging concept. In everyday life, we are accustomed to thinking that small events lead to small outcomes and large events lead to large outcomes. However, in chaotic systems, this linear relationship does not apply. A small change can grow exponentially over time, ultimately steering the system in a completely different direction. The discovery of the butterfly effect posed a direct challenge to Laplace's deterministic view of the universe. According to Laplace, a being that knew the exact state of the universe could predict the future with certainty. However, the butterfly effect showed that this idea is practically impossible. In chaotic systems, the smallest uncertainties in initial conditions grow over time, eventually leading to entirely different outcomes. This means that even Laplace's demon could not predict the future with certainty because it would be impossible to know the initial conditions with infinite precision. Moreover, the butterfly effect not only makes predicting the future difficult, but it also makes reconstructing the past equally impossible. Starting from the current state of a system, it would be just as hard to determine its exact past state. This doesn't entirely disprove determinism, but it does impose significant limitations on it. The universe may still be deterministic, meaning that every event could be the result of prior events governed by physical laws. However, this determinism does not necessarily translate to practical predictability. The discovery of the butterfly effect largely stems from Edward Lorenz's work in the 1960s. Lorenz was a meteorologist and mathematician working at the Massachusetts Institute of Technology. He was developing a simple computer model to improve weather predictions. Lorenz's model used 12 key variables, such as temperature, pressure, and humidity, to simulate the behavior of the atmosphere. One day, Lorenz wanted to rerun a simulation, but to save time, he input numbers from the middle of a previous run. He expected the new simulation to produce the same results as the earlier one. However, Lorenz noticed something surprising. The new simulation soon began to deviate entirely from the previous one. At first, he thought there was a mistake in the computer, but upon closer examination, he discovered that the real cause was a tiny difference in the initial values. Lorenz realized that the computer was calculating to 6 decimal places, but the output displayed only 3 decimal places. When he restarted the simulation, he used the shortened numbers, creating a minuscule difference in the initial conditions, only in the 6th decimal place. This small difference grew over time and eventually produced an entirely different weather prediction. Lorenz immediately recognized the significance of this discovery. In complex systems like the weather, even the tiniest uncertainties in initial conditions can make long-term predictions impossible. Lorenz's discovery laid the foundation for chaos theory and led to the development of new mathematical tools. One of these tools is the mathematical structure known as the Lorenz attractor. The Lorenz attractor is a powerful tool for visualizing and understanding the behavior of chaotic systems. The Lorenz attractor describes the motion of a system in phase space. Phase space is a multidimensional graphical representation of all possible states of a system. Each point represents the state of the system at a particular moment. The Lorenz attractor, with its butterfly-shaped structure, perfectly illustrates the fundamental characteristics of chaotic systems, and this visual resemblance contributed to the popularization of the term butterfly effect. This mathematical structure reveals 3 key features of chaotic systems: non-periodicity, meaning the system never returns to the exact same state; boundedness, meaning the system stays within certain limits rather than diverging to infinity; and a fractal structure, where the attractor displays complex, self-similar features at every scale. These features explain why the Lorenz attractor is such a powerful tool for understanding and visualizing the nature of chaotic systems. The complex motion in phase space shows just how sensitive chaotic systems are to their initial conditions. 2 paths that start very close together can diverge dramatically over time, leading to entirely different trajectories. This is a visual representation of the butterfly effect. The Lorenz attractor and phase space analysis provide powerful tools for understanding the behavior of chaotic systems. These tools are used in a wide range of fields, from weather forecasting to economic modeling. brain activity to ecological systems. The butterfly effect and chaos theory largely limit, and in some cases make impossible, the full knowability of reality. This has led to a significant paradigm shift in our scientific understanding. First, the butterfly effect shows that long-term predictions in complex systems are impossible. In many important fields, such as weather forecasting, climate science, ecosystems, and economics, it is impossible to make exact predictions beyond a certain time horizon. This has profound implications for how we understand and manage the behavior of these systems. Second, the butterfly effect reveals that there can never be a definite definition of reality. No measurement, no matter how precise, can be entirely free from uncertainty. In chaotic systems, these small uncertainties grow over time, eventually changing the behavior of the system entirely. Third, the butterfly effect demonstrates that even if the universe is deterministic, it may still be practically unpredictable. This adds a new dimension to philosophical debates about free will and determinism. Even if the universe is fully determined, this determinism does not necessarily equate to predictability. That is, while the universe's rules may be deterministic, chaotic processes can make outcomes so complex that they become impossible to predict. This raises new questions about human actions and free will. If the universe is deterministic, but we cannot fully know its outcome, how does that affect free will? Perhaps the existence of free will can find a space within the universe's unpredictable nature. The holographic universe theory suggests that space and time could be surface-level reflections of a more fundamental structure. According to this theory, the three-dimensional structure of the universe is actually the result of information encoded on a two-dimensional surface. The idea that the fabric of space arises from something deeper gains significance. Space and time are not fixed, absolute structures, but rather emerge from a more fundamental, quantum, mechanical, or holographic structure. This proposal may be unsettling because it challenges traditional views about the nature of existence. It suggests that the three-dimensional reality we perceive is actually a projection of a two-dimensional surface. According to the holographic principle, all the information in the universe is encoded on a two-dimensional surface, and the three-dimensional reality we perceive is a reflection of that surface. The nature of space has been one of the most fundamental and long-standing questions in physics. Isaac Newton thought of space as a fixed, absolute, and unchanging structure. However, modern science, particularly with quantum gravity theories, proposes that space has a dynamic and changeable nature. The fundamental goal of physics is to discover and understand the most basic building blocks of the universe. This includes determining how physical reality operates at its most fundamental level, including the nature of space and time. The nature of space and time lies at the core of these building blocks. Modern quantum gravity theories propose that space emerges as a result of more fundamental quantum structures. These theories suggest that space is not a building block itself, but rather the product of interactions at the quantum level. Space emerges from these interactions and has a dynamic nature. This understanding has been expanded through studies of the thermodynamic properties of black holes. The relationship between black hole entropy and surface area is directly connected to the dynamic nature of space and gravity at the quantum level. The groundbreaking work of Bekenstein and Hawking showed that black hole entropy could be calculated, and that the laws of thermodynamics apply to black holes. The entropy of black holes is extremely large because they store information about the matter that falls into them, and this entropy is proportional to the surface area of the event horizon. In this framework, as the surface area of a black hole increases, so does the amount of information it can store. According to Bekenstein and Hawking's calculations, a black hole's entropy contains approximately 1 bit of hidden information for every 4 square Planck units of surface area. This finding establishes a strong link between quantum gravity and information theory, helping us understand how the universe's fundamental building blocks relate to information. Finally, the Bekenstein bound determines the maximum amount of information that can be stored, proportional to the surface area of a black hole. This limit is not only related to black hole entropy, but also to broader concepts of the nature of space, time, and information. The relationship between the surface area of black holes and entropy reveals how quantum structures and space are dynamically intertwined in our modern understanding of physical reality. These findings showing that information is stored on the surface rather than in the volume of black holes, suggested that the universe could operate under a similar principle on a broader scale. This understanding was translated into a more general theory of physical reality through the holographic principle. At the heart of the holographic principle are studies on information theory and black hole entropy. In black holes, it is understood that all the information that falls into them is stored at the event horizon, and this information is proportional to the surface area of the black hole. This result shows that information can be stored on a surface rather than in a volume. The correspondence between anti-de Sitter space and conformal field theory is one of the strongest theories embodying the holographic principle. This theory suggests that the universe is encoded in anti-de Sitter space, and the information on two-dimensional surfaces gives rise to three-dimensional structures. The theoretical framework shows that physical processes in the universe can manifest as three-dimensional structures based on information on a two-dimensional surface. Anti-de Sitter space is a space with negative curvature, and conformal field theory is used to understand how physical processes operate in this space. Conformal field theory is a theory that describes how objects interact regardless of their dimensions or scales, and reveals how physical processes in the universe are similar across different scales. This correspondence builds a bridge between quantum mechanics and general relativity, providing a deep understanding of how the universe fundamentally operates. The holographic principle suggests that space is a reflection of information on a more fundamental surface, and that the three-dimensional structure can be thought of as a projection of the information on this surface. How space can be represented at different scales is explained through patterns and degrees of freedom. Nested spheres are used to explain how the structure of space at different scales is represented. Each sphere represents a different scale of space, and information is stored across these scales. Pattern dimensions are the fundamental components that make up the holographic structure of space. These patterns create structures that carry information at different scales within space, and each pattern stores information in a particular part of space. The nature of holographic duality is still not fully understood. Duality is a situation in which two different physical theories can describe the same universe in different ways. Holographic duality raises the question of whether both theories are equally valid and whether it can be considered a true duality. Holographic duality suggests that mass may be a phenomenon emerging from a boundary, which is based on the idea that everything in the universe is encoded on the boundary. Understanding whether the universe has a holographic duality depends on the mathematical results of these theories and their alignment with observational data. The holographic structure of the universe is a field that requires further research. Concepts such as entropic gravity and quantum entanglement can help further understand this structure. Entropic gravity is a theory that suggests gravity is related to entropy, and that the structure of space emerges from this relationship. Some theories propose that the holographic boundary might emerge in the distant future of our universe, which could happen when the universe undergoes extreme expansion. The perception of space and time is one of the most fundamental concepts in physics. Throughout history, physics has challenged and overturned our intuitions. Modern physics, particularly quantum mechanics and general relativity, has shown that space and time may not be as simple and fundamental as once believed. At very small scales, especially at the Planck scale, defining space and time meaningfully becomes nearly impossible. This scale is about 10 to the power of minus 35 meters and 10 to the power of minus 43 seconds, 20 times smaller than the smallest known atomic nucleus. This has led physicists to consider that space and time might emerge from more fundamental structures. Interestingly, some theories propose that space could have a kind of foam-like structure. According to the quantum foam theory, at the Planck scale, space is not continuous, but filled with microscopic holes and bubbles that continuously form and disappear. This idea opens new ways to understand the structure of space. The question of whether space and time are truly fundamental concepts forms one of the most exciting research areas in modern physics. This question is significant not only in theoretical physics, but also philosophically. Our understanding of space and time has undergone continuous evolution throughout human history. Ancient Greek philosophers viewed space as a relational concept. For example, Aristotle associated space with place and argued that a vacuum could not exist. In the 17th century, René Descartes' coordinate system allowed space to be represented mathematically. This was a revolutionary development in physics and mathematics. Descartes' discovery was the precursor to the three-dimensional coordinate system, which forms the basis of modern GPS systems. Isaac Newton saw space and time as absolute, unchanging, and independent entities. Newton's view introduced the concepts of absolute space and absolute time, which dominated the world of physics for more than 2 centuries. On the other hand, Gottfried Wilhelm Leibniz opposed Newton's view, seeing space and time as relational. Leibniz's view can be seen as a precursor to the modern concept of relativity, which plays an important role in contemporary physics. Interestingly, Leibniz also developed the binary number system, which forms the foundation of modern computers. This historical development shows how complex and debated the concepts of space and time have been. Each new theory has reshaped and deepened these concepts. The discovery of electromagnetism and the development of field theory led to revolutionary changes in our understanding of space-time. In the 19th century, James Clerk Maxwell's work showed that electricity and magnetism were actually different aspects of the same phenomenon. This unified theory gave rise to the concept of the electromagnetic field and suggested that space might not be empty. The field concept became increasingly central to physics theories. In addition to the electromagnetic field, modern theories like quantum field theory described space as an environment where various fields exist. These fields form the basis of particles and forces. Interestingly, the discovery of electromagnetic waves led to the belief in a hypothetical substance called ether. Scientists thought light needed a medium to propagate. However, the famous Michelson-Morley experiment disproved the existence of ether, paving the way for Einstein's theory of special relativity. With the development of quantum mechanics, the idea emerged that even empty space could possess a kind of energy. This concept of vacuum energy further deepened our thoughts about the structure of space. Some theories suggest this energy might be the source of dark energy, responsible for the acceleration of the universe's expansion. Albert Einstein's theories of special and general relativity led to revolutionary changes in our concepts of space and time. The theory of special relativity showed that space and time could not be considered separately. According to this theory, the flow of time depends on the speed of the observer. This phenomenon, known as time dilation, is a factor that must be considered in GPS satellites. The theory of general relativity, however, revealed that space-time is a flexible structure that can be bent by mass and energy. Einstein described gravity as the curvature of space-time. This idea was so radical that even Einstein initially hesitated to accept some of the consequences of his theory, such as the existence of black holes. Einstein's theories combined space and time into a 4-dimensional concept known as space-time. This 4-dimensional structure is known as Minkowski space and is one of the cornerstones of modern physics. Interestingly, this concept has been embraced by science fiction writers, contributing to the popularization of the idea of time travel in popular culture. The theory of relativity showed that space and time are not absolute. They change depending on the motion and position of the observer. This completely transformed Newton's concepts of absolute space and time. There was no longer a universal now. The flow of time could vary based on the observer's movement and the gravitational field in which they are located. Modern physics, particularly through the development of quantum mechanics and general relativity, has made our understanding of space-time more complex and mysterious. These two theories become incompatible at very small scales. This inconsistency has led physicists to search for a theory of everything. Quantum mechanics suggests that particles can exist in multiple places simultaneously. This concept of superposition has raised new questions about the nature of space. Furthermore, the phenomenon of quantum entanglement, what Einstein referred to as spooky action at a distance, challenges our understanding of space-time. String theory proposes that all fundamental particles are actually very small vibrating strings. This theory attempts to reconcile quantum mechanics and general relativity by increasing the number of dimensions of space to 10 or 11. Why we cannot observe these extra dimensions remains a mystery. Some theories suggest these dimensions are curled up. Loop quantum gravity, on the other hand, proposes that space-time is made up of small, discrete quantum units. According to this theory, space and time are not continuous but discrete. This suggests that space-time may have a kind of lattice or network structure at its most fundamental level. On the other hand, modern neuroscience research provides important insights into how the brain constructs the perception of space and time. Brain regions such as the hippocampus play a critical role in this perception. The hippocampus is essential for both spatial navigation and the temporal ordering of events. The importance of these findings was underscored when the 2014 Nobel Prize in Physiology or Medicine was awarded for the discovery of the brain's positioning system. Neurons called grid cells and place cells provide deep insight into how the brain perceives our environment and determines our location. These cells allow the brain to organize an individual's relationship with physical space based on environmental cues. It is also known that cultural factors and language influence the perception of space and time. For example, some Amazon tribes perceive time not as a linear process, but as a cyclical concept, perhaps due to their lives being in harmony with ritual and natural cycles. Similarly, language structure shapes perception. In languages like Chinese, time is expressed through vertical metaphors, where the future is up and the past is down, while in English, time is conveyed through horizontal metaphors, with the future ahead and the past behind. These linguistic differences provide important clues about how people structure their concept of time and suggest that the perception of space-time can be shaped by language. These findings suggest that space and time might not be universal and objective concepts, but rather tools organized by the human mind, which vary depending on cultural context. Humans use these concepts to understand their surroundings and organize their lives. This shows that the perception of space and time is a construct shaped by neurological mechanisms developed through evolutionary processes, as well as cultural elements. In conclusion, modern neuroscience and cultural studies suggest that space and time are not fixed and universal realities, but cognitive frameworks that we have developed to understand our environment and organize our lives. This perspective supports the idea that space and time are not absolute realities, but tools constructed by the human mind to make sense of the world. When the brain's functioning, evolutionary development, and cultural factors are combined, we see that the perception of space and time is flexible and variable. Life and death have always been profound mysteries in the human mind. People have asked various questions about the beginning and end of existence, especially delving deeply into whether death is an end or a continuation of existence in another form. At this point, the biocentric perspective offers a different approach to the role of consciousness in the universe, redefining the cycle of life and death, the nature of time, and the role of consciousness after death. This approach suggests that death is not an end, but rather the beginning of existence in a new form for consciousness. So, within the framework of biocentric theory, how does the perception of time change at the moment of death? How can memories persist after death? And how is the role of consciousness defined? According to the biocentric perspective, the perception of time in the universe is directly related to consciousness. In the traditional understanding, time is accepted as a linear flow. There is a clear distinction between past, present, and future. However, biocentrism argues that time is not linear, but rather a perception created by consciousness. In this context, at the moment of death, the perception of time by consciousness may radically change. In moments of danger or near-death experiences, many people report feeling that time has slowed down or stopped entirely. According to the biocentric approach, such experiences reveal the ability of consciousness to restructure its perception of time. At the moment of death, when consciousness becomes independent of the physical body, the perception of time may completely disappear or transform into a new form. This aligns with the idea that death is a transition of consciousness to a different dimension, and that time is a concept limited to physical existence. When reflecting on concepts of consciousness and time after death, the question of how memories and past experiences can exist also arises. Biocentrism supports the possibility of memories continuing to exist after death by arguing that time is merely a product of consciousness. Assuming that consciousness continues to exist as an independent form of energy from the physical body, memories and past experiences could also persist alongside this consciousness. Considering that time is not a linear reality, but rather a structure dependent on the perception of consciousness, according to biocentric theory, memories may continue to exist in universal consciousness, even after the death of the physical body. When the past and future are seen as concepts created solely by the mind, it is possible that memories may find a different place within this new form of consciousness. Biocentrism's understanding of post-death consciousness is based on the idea that consciousness transforms into a universal form of energy, or merges with universal consciousness. This approach strengthens the argument that individual consciousness maintains its relationship with the universe, and that death is not the end, but a transition to a different form of existence for this consciousness. Consciousness continues its existence beyond the physical body, remaining a part of the universe even after death. This view, which aligns with quantum theory and the observer effect, supports the idea that consciousness is not merely an observer, but also shapes physical reality. Therefore, the continuation of consciousness, playing a role in universal processes, even after death, redefines the relationship between consciousness, time, and the universe. Consciousness, as it transitions from one form to another, integrates into the universal consciousness and continues to exist. From a biocentric perspective, the transformation of the perception of time at the moment of death, the existence of memories, and the continuation of consciousness after death challenge traditional notions about the structure of the universe. Time is a concept created by biological entities and only gains meaning as long as consciousness exists. At the moment of death, the perception of time may disappear or continue to exist in a different dimension. Memories and past experiences may continue to exist in a universal structure through the continuity of consciousness. The role of consciousness after death can be defined as a process of merging or interacting with universal consciousness. In this framework, biocentrism approaches the cycle of life and death from a broader consciousness perspective, allowing us to view existence as an infinite cycle of consciousness.